Hello and welcome to this video in which I will walk you through an example latent state trait analysis. My name is Geiser, I'm an instructor with QuantFish, and on this channel I present weekly statistics tutorials. I usually talk about multivariate statistical methods including structural equation models, factor models, multi-level analysis and latent class modeling. If this is something that interests you, then please subscribe to this channel. Also, don't forget to hit the like button and to check out the description for additional resources, including a link to my free weekly statistics newsletter, as well as courses that I teach for QuantFish. In this video, I want to show you an example of a latent state trait analysis. So let's get right into it. What is a latent state trait model? A latent state trait model is a longitudinal confirmatory factor analysis model, or you could say a longitudinal structural equation model that allows us to separate trait, state, and error components in longitudinal data. So what does that look like? Let's take a look at an example model. So here we have a single factor with the label tau1 here and three indicators, y1, y2, and y3. So those could be, for example, three different items for measuring mood states, for example, positive affect, or they could be scale scores, questionnaire scores. And so we're measuring these scores repeatedly across time. You can see that these indices here, or these variables, have the second index 1 for time point 1. And so now we're assuming that we have at least one other time point where we are measuring the same indicators, or at least partially the same indicators, the same items again. So you can see now they have the index 2 here at the end for the second time point, and otherwise those are the same questions or the same indicators. And so this right now would be a longitudinal confirmatory factor analysis model where we would typically allow the factors to be correlated over time to model the stability of inter-individual differences across time, to see how stable the rank ordering of individuals is across time. In latent state trait analysis, we explain the correlations of the factors across time by trait factors, or by one trait factor in this case. So in this case, in this parameterization of a latent state trait model, the trait factor Xi is a higher order factor that accounts for that covariance of tau1 and tau2 across time. And so it basically absorbs the stability in the data, the stability across time, and reflects that stability. That's why it's called a trait factor. So that is the factor that represents consistent or person-specific inter-individual differences across time. In addition, we have so-called state residuals, zeta 1 and zeta 2. So those are the residual variables of the first order factors tau1 and tau2. And they reflect time-specific or situation-specific influences, also person-by-situation interaction effects, if there are any. Those are all reflected by zeta 1 and zeta 2, the time-specific residuals. So essentially what this is here is a second-order factor model for longitudinal data where the second-order factor represents the stability across time, and the first order factors are broken down, so to say, into the stable aspect that's represented by the trait and situation specific variance that is represented by zeta 1 and zeta 2. And in addition, we have error variables, epsilon, here at the bottom, that represent measurement error. As we will see shortly, this model allows us to decompose the variance into trait variance, situation-specific variance, and measurement error variance or unreliability. So in terms of a structural equation, we can say that the first order so-called state factors tau1 and tau2 are broken down into a common trait factor Xi and a state residual factor zeta t. And as we'll see on the next slide, this allows for a variance decomposition because the trait psi and the state residual zeta t are uncorrelated, so they provide independent sources of variance in tau 1 and tau 2, and so their variance components can be separated. Now, this is a prototypical classical latent state trait model parameterized as a second order model. There are many other kinds of ways in which you can specify a latent state trait model. There are different versions that differ in how restrictive they are and how much they model indicator-specific effects, if there are any, and some are based on first-order parameterizations. They don't have a second-order trait factor, but instead the variables load directly onto trait factors. I also have a video on this channel about an indicator-specific trait LST model, where I describe a model where you don't have the second-order parameterization, so you can check that out as well. And I have an entire playlist on this channel as well on latent state trait models that you're welcome to check out. So let's continue with this prototypical LST model specified as a second order factor model, because it makes it easy to understand how this works and what the output looks like when you're a beginner with latent state trait models. Then this is a good model to start with to get a sense for what LST models do. The variance decomposition is one of the key elements of a latent state trait analysis. So we want to distinguish between trait variance, or we want to separate trait variance from situation specific variance, and we can do this based on the model implied variance decomposition of the true score or latent state variance. So the variance of the first order factors tau t can be broken down into variance that is due to the trait factor plus variance that is due to the zeta state residual factor, because these two are not correlated, so they provide independent sources of variance, and we have an additive variance decomposition. Based on that additive variance decomposition, we can define R-squared type coefficients that allow us to quantify trait variance or consistency, first of all, where consistency indicates that proportion of true score variance that is stable across time. It is calculated or can be defined as the ratio of the trait factor variance over the variance of tau t, where the variance of tau t can be calculated as the sum of those two variance components as shown here in the true score variance decomposition. And so this coefficient, the consistency coefficient, is equal to the R-squared for the latent variable that you can obtain, for example, in Mplus when you run such a model as a second order factor model. As we will see, Mplus will give you an R-squared for the first order factors, and so that R-squared is equal to consistency and gives you the proportion of true score variance that is trait variance. So let's say, for example, you find that consistency is 0.7, then this would mean that 70% of the variance in the first order factors is trait variance and only 30% of the variance in the first order factors is situation specific variance. So that would then indicate that the construct is more trait-like than state-like. Furthermore, we have the occasion specificity coefficient, which accounts for the remaining portion of true score variance. Occasion specificity is defined as the ratio of zeta variance to first order factor variance and is equal to 1 minus R-squared latent variable. And so that gives us the remaining proportion of variance that is not accounted for by the trait factor. Let's take a look at how a model like this can be analyzed in software for structural equation modeling, specifically Mplus. You can also run this model in any other software that allows you to run confirmatory factor analysis or structural equation modeling, such as Latent, AMOS, Lisrel, EQS, MX, and so on. So the Mplus syntax for a model like this is very straightforward. In the model statement, you have your factor, your first order factors first. Tau 1 is the factor for time point 1. You can see here that I specified this model with equality restrictions on the loading. So the labels L2 and L3 here are to hold the loadings equal across time. The first loading is always fixed by default in Mplus to identify the model. So this loading is fixed to 1. The other loadings will be estimated, but we will constrain them to be equal to the loadings at time 2. You can see the corresponding loadings here for tau 2 have the same label L2 and L3, so that these loadings will be time invariant for measurement invariance across time. Now, this is not strictly necessary in an LST model, but it often makes sense and it makes the model more parsimonious. Of course, it's something that should be tested first, whether measurement invariance is acceptable here. And then next we specify the second order factor in the same way, xi by tau 1, tau 2, and both loadings here in this case have to be fixed to 1 because we have only 2 time points, and with 2 time points we have only 2 first order factors, so the xi second order factor has only 2 indicators, and so the model would be under-identified if we estimated one of the loadings freely unless the trait was correlated with some other variable in the model, in which case that would help. But since here we have an unconditional model, or a model where xi is not correlated with other variables, we have to fix both loadings to 1 to identify the model. That would be different if you had 3 or more time points, in which case those loadings need not be fixed to 1, not all of them, because then the model would be identifiable even with some of the loadings freely estimated. And so that's the entire specification. If we focus on the covariance structure, which is most of the time that's what's of most interest in latent state trait modeling, to look at the covariance structure and the variance decomposition. In this case, I left out the mean structure. The mean structure can also be modeled, but often it's not of such great interest in LST analyses. Now let's take a look at the output and let's see how we interpret the parameters that Mplus spits out for an LST model like that. So the first part that I want to look at, and I'm not going to show you all the output because it's a lot and you have a lot of unstandardized estimates and standardized estimates. I'm only going to focus on the estimates that are most relevant, especially for beginners, most relevant to look at, and that tell you the key results that you would want to know about when you run a latent state trait model. And so that would include looking at the standardized loadings. Of course, it would first of all also include looking at model fit. In this case, this model fits very well. The chi-square is not significant, so we can interpret the parameter estimates. And so the standardized loadings in Mplus are found under the STDYX standardization. So this means they are completely standardized loadings where both the observed and the latent variables are standardized to unit variance. And so these loadings have a very clear interpretation in a latent state trait model like this. First of all, we get the loadings of the indicators or observed variables on the first order factors here shown for the time 1 factor, tau 1. You can see all those loadings are very strong between 0.898 and 0.94. So that indicates that those indicators are highly reliable. The squared standardized loadings, as we will see later, are given under R squared in Mplus, and those give us the reliabilities of the indicators. The same is true for the indicators at time 2. You can see the loadings are very similar, again between 0.887 and 0.959, so very similar to the loadings at time 1 and very strong, indicating that these indicators don't have a lot of error variance. And then also we get the standardized loadings on the Xi factor, and notice that these are not equal to 1, even though we fixed the unstandardized loadings to 1, and they're also not equal. So the standardized loadings can still differ even if we have to fix the unstandardized loadings both to 1, because there are differences in the variances of tau 1 and tau 2, and so those loadings need not be equal, but they're very similar and they're very strong. So you can see they're 0.942 and 0.959, indicating that the Xi factor is very strongly related to the first order factors. These loadings give us the correlations between Xi and tau 1 and tau 2 in the same way as the standardized first order loadings give us the correlations between the observed variables and their latent variables, the first order factors. So this therefore, so say later on we'll see R squared is based on the squared standardized loadings, because these indicate R, the correlation, and then R squared is equal to those loadings squared. So what this means is that Xi is correlated 0.959 with tau 1 and Xi is correlated 0.942 with tau 2. That's very strong. And so what that indicates is that this construct is mostly trait-like. So the trait accounts for most of the variance in tau 1 and tau 2. We can already see that even though those values are not R squared, they are equal to R, not R squared, but you can already imagine that these values squared will give you something that's very, very high, close to 0.9, as we will see later. So this already shows us that this construct is much more trait-like than state-like. There's not much of a situational component here. So this could be, for example, scores on an intelligence test or cognitive abilities test, or another very stable personality trait that does not show much fluctuation across situations. Let's take a look at other output. And so the next thing that I want to show you are the standardized residual variances from the Mplus output. Again, this is the STD-YX standardization. And so the residual variances give us, first of all, a sense for the unreliabilities of the observed variables. So in Mplus, the standardized residual variances that you find here under estimate, those give you 1 minus R squared, or 1 minus reliability for the observed variables. And so this shows you that only between 7.9% and 21.4% of the variance in the observed scores is error variance. So for the most part, more than 80% or close to 80% or more of the variance in the observed scores is reliable or true score variance. So these measures are very reliable. That's what that shows us. These values give us 1 minus reliability, or 1 minus R squared. And so this corresponds to the very strong standardized loadings that we saw on the previous slide for the observed variables on the tau 1 and tau 2 factors. Furthermore, we also get the residual variances for tau 1 and tau 2. And those have a specific meaning because they give us 1 minus R squared for the latent variables, so for the first order factors. And so that's equal to occasion specificity, as we saw previously. So the occasion specificity in the LST model is the variance that's explained by zeta, by the state residual factors, zeta 1 and zeta 2. And that's what you get in Mplus under the standardized residual variables for residual variances, for tau 1 and tau 2. So what this means is that 8.1% of the true score variance at time 1 and 11.3% of the true score variance at time 2 was occasion specific variance or situation variance. And so the remaining about 90% of the variance were trait variance. Okay, so this gives you already occasion specificity for the latent variables as shown here, again, based on this formula that I already showed you earlier. So you can always find the occasion specificities under the standardized residual variances in Mplus when you run an LST model as a hierarchical or second order factor model, and that's really practical because then you don't have to compute them yourself. Furthermore, we get R squared in Mplus, and the first portion of the R squared is for observed variables. So that's for the YIT indicators, for the Y variables. And so those are the standardized loadings squared. We already saw earlier that the standardized factor loadings of the y variables were very strong. And so here now you can see those loadings squared, which give us R squared, or reliability in the sense of latent state trait theory. And so you can see that the reliabilities ranged between 0.786 and 0.921. So between 78.6% and 92.1% of the observed variance represented true score variance. And so that's good reliability. You can interpret that in the same way as you would interpret a classical test theory based reliability index in terms of the proportion of true score variance relative to observed variance. Furthermore, we get the consistencies for the latent variables, and those are given in Mplus under R squared for the latent variables. So here you can see those estimates here for tau 1 and tau 2 under R squared are the squared standardized second order factor loadings, which we saw were both above 0.9. And so those give you then R squared values between 0.887 and 0.919, indicating that between 88.7% and 91.9% of the latent variance of the first order true score variance was trait variance. So most of the variance in the tau 1 and tau 2 time-specific factors represents trait variance. This is a very trait-like construct such as intelligence. So if you ran an LST model on an intelligence test that was measured at 2 time points, you would find similarly high consistency coefficients, probably if not even higher, because intelligence tests tend to have very high stabilities across time, very high correlations of the true scores across time, and so there's not much situation-specific variance involved when people take intelligence tests. So that gives you consistency for the latent variables. Again, that's practical because then you don't have to calculate that by hand. You can just simply look at the R squared for the latent variable, and then that gives you the consistency. The consistency is the proportion of trait variance that is explained, or proportion of variance in the first order factors that is explained by the second order trait factor. I hope you found this video useful to learn about LST models and how they work and how the output is interpreted for LST models. If you did, then please subscribe to this channel and don't forget to check out the description for additional resources, including a course on latent state trait models that I teach for QuantFish, and I'll see you next time.